Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. Let's see this problem. We are given two numbers a and b, and our task is to find how many bits needs to be flipped to convert a to b. So to understand this problem, let's see few examples. So in first example, we have two numbers a and b. A is equal to 8 and b is equal to 7. Binary representation of number 8 is 1 0 0 0 and binary representation of number 7 is 0 1 1 1. So if you look at this binary representation, if we want to convert number 8 to number 7, we need to flip 4 bits. We have to convert this 0 to 1, this 0 to 1, this 0 to 1 and this 1 to 0. It means 4 bits need to be flipped. So the output of this input is 4. Let's see next example. In this example, we have a and b is equal to 2 and 5. The binary representation of number 2 is 0 0 1 0 and 5 is 0 1 0 1. So in this case, if we want to convert 2 to 5, we need to flip this bit, then this bit, then this bit, right? So number of bits needed to convert 2 to 5 is 3. So the output of this input is 3. So now you have a good understanding of this problem. So let's pause this video and think about an algorithm to solve this problem. So I hope by now you would have written at least brute force approach to solve this problem. So let's see the brute force approach to solve this problem. The idea is pretty simple. What we do, we simply traverse both the numbers from least significant bit to most significant bit. And in each iteration, we check if bit is alternating or not. If we found that bit is alternating, we simply increment counter by 1. And after that, we simply right shift bit by 1 position so that we can check next bit. And we are going to repeat all these steps till number becomes 0. And we already know how to right shift bit using bitwise operator. Okay. So this is the basic idea. Now let's see the implementation of brute force approach. So here we have a function count diff bits. This function is taking two inputs a and b. In first line we are initializing count variable to 0. Then we are running a loop while a is greater than 0 or b is greater than 0. In each iteration we are checking if both the bits are alternating or not. It means if a and 1 is not equal to b and 1, it means one bit is 0 and one bit is 1, right? In that case, we are incrementing count by 1. And after if statement, we are simply right shifting both the numbers by 1 position. And then at the last, we are returning count. Okay? And in this while loop, we are checking if a is greater than 0 and b is greater than 0. Why? Because it might be possible that one number becomes 0 early than the other number. That's why if any of the number is greater than 0, then we are simply continue this loop. Okay, so let's quickly dry run this code and see how it works. So let's say if a is equal to 8 and b is equal to 7, the initial value of count is 0. Binary representation of number 8 is 1 0 0 and binary representation of number 7 is 0 1 1 1. So in first iteration, we check if both the bits are alternating, and this time both the bits are alternating. So we are incrementing count by 1. And then we shift both the numbers by 1 place towards right. So now the binary becomes 0 1 0 0 and 0 0 1 1. In second iteration, again we check if the bits are alternating. This time also it is alternating. So we are incrementing count variable by 1. So it becomes 2. And then we are shifting a and b towards right. In next iteration, we are again checking if bits are alternating or not. And we are incrementing count again by 1. So count becomes 3. And then we are doing right shift on both the numbers. In next iteration, we again check if the bits are alternating, and it is. So we are incrementing counter by 1. So value of counter becomes 4. And then we shift both the numbers. Now this time both the numbers becomes 0. So the condition in this while loop becomes false and we come out of this loop. And in the last, we simply return value of count variable, that is 4. So 4 gets printed on the screen. Okay, great. So let's talk about time complexity of this solution. To calculate time complexity of this function, we have to find how many times the loop is running. So this loop is running exactly equal to number of bits present in the number. So that is why the overall time complexity of this function is going to be big of number of bits. Why big of notation? Because in worst case you get this number like 1111 and you want to convert this number to b. So in this case you have to traverse all the bits, right? And you can see in this example also, we are traversing all the bits. If there are 4 bits, then we have to traverse 4 times. And if there are 32-bit integers, then we have to traverse all the 32 bits to convert that number into desired number. Okay, that is why the time complexity is big of b, and this is the upper bound. Okay, so far so clear. But here I think that we can do much better. So think about a bitwise operator. Can we use any bitwise operator so that it can help us to solve this problem in less time complexity? Do we know any such bitwise operator? Think about it. So now let's talk about the efficient approach to solve this problem. So the idea for efficient approach is, let's say we have two numbers a and b. The a is equal to 2 and b is equal to 4. Binary representation of number a is 0010 and for b is 0100. Now if I ask you how many bits we need to flip to convert 2 to 4, then you can simply say 2 bits. Why? Because here there are 2 alternating bits and we need to flip this bit. Okay, and here also we have one alternating bit and we have to flip this bit. So here you can see there are 2 markers that tells us that in these positions you have to flip bits. So now think about a bitwise operator that can help us in finding these markers. So here we can use XOR operator. Why? Because XOR operator work exactly like this. So when we do bitwise XOR of 2 alternating bits, it gives us 1, right? If we XOR 0 and 1, it gives 1, and if we do 1 XOR 0, it gives 1. In all other cases, it simply gives 0. So when we do XOR of a and b, we get 0, 1, 1, 0. It means there are 2 bits that needs to be flipped to convert a to b. Clear? So now our problem reduces to count set bits in this number. And we already know how to count set bits in a given number. We simply use Brian-Kernigham's algorithm to find number of set bits in a given number. So I have explained Brian-Kernigham's algorithm in detail in previous videos. If you have not watched that video, then I highly recommend to watch that video and come back here and continue watching this video. You can find link of that video in this playlist only. So still, just to give you an idea, let me recall once again. So what Brian-Kernigham's algorithm says, if you do bitwise AND of n with n-1, the rightmost bit of the number n gets unset. So this is the simple algorithm. So in case of this number, we just have to call Brian-Kernigham's algorithm 2 times, right? And our number becomes 0. And this 2 iteration is exactly equal to number of bits needs to be flipped. Let me show you how. So this is the implementation of efficient approach. In this approach, here we have a function. This function is taking 2 inputs a and b. In first statement, we are doing a XOR b to get the markers or to get the set bits. And then we are initializing a count variable to 0. And then we are running a loop while n greater than 0. And in each iteration, we are simply incrementing count variable by 1. And then we are performing Brian-Kernigham's algorithm. And at the last, we are simply returning value of count variable. So let's quickly dry run this code and see how it works. For a equal to 2 and b equal to 4, the initial value of c is 0. After we perform XOR operator, our n becomes 0, 1, 1, 0. Clear? Now our loop begins. In first iteration, the value of count becomes 1. And after performing Brian-Kernigham's algorithm, the rightmost bit becomes unset. So the binary representation reduces to 0, 1, 0, 0. In next iteration, our C becomes 2. And in this iteration, the rightmost bit gets unset. So the binary becomes 0000, and this is equivalent to decimal 0. In next iteration, our n is not greater than 0. So the loop gets stopped and we simply return. So for these two values, the output is 2. Okay. Now talking about time complexity of this function, how many times loop is running? So as you can see that if the number has 2 bits, then loop runs 2 times. If any number has 3 bits, 3 set bits, it means loop runs 3 times. So we can say that the time complexity of this function is big O of max of log A and log B. Why we are doing log? Because when we do log, we can easily get the number of bits needed to represent any number. And why we are doing maximum? Because the fact is, when a number is greater, then probably that number is going to have more bits set or more set bits, right? In the worst case, okay? Here we are talking about worst case only, okay? We are not considering best case because we are not clear what are the numbers will be, okay? So this is about time complexity. Now what about space complexity? As this is an iterative solution, we are not using any auxiliary space other than some variables. So that's why the space complexity of this solution comes out to be theta of 1. So we are taking constant space to solve this problem. So far so clear. I hope you got it. So before we end this video, let's have a quick recap of what we have done so far. So we are given two numbers A and B, and our task is to find out how many bits needs to be flipped to convert A to B. We saw the brute force approach to solve this problem. In this approach, the time complexity came out to be big of number of bits present in the number. After brute force approach, we saw the efficient approach to solve this problem. And in this approach, the time complexity comes out to be big of max of log A, log B. So I hope you really understand the problem and both the approaches really well. So this is it for this video. Thanks for watching and see you in the next video.